Thanks for coming. So, in the 1920s, a spectre was haunting quantum physics. This was the Gruppenpest, or the plague of group theory. So this is a part of abstract algebra, and a number of physicists at the time, including Hermann Weyl, had been using it to calculate atomic spectra. Oh, sorry, it's auto-advancing. But not everyone was happy. There was a lot of resistance. Few wanted to learn this new branch of maths, which they felt was too abstract and an interloper into the world of physics. Then John Slater worked out how to do the calculations without using group theory, and physicists were triumphant. Slater had slain the Gruppenpest. But in fact, it was only sleeping. And then we fast forward to the 1960s. Group theory isn't part of the curriculum for physicists, but in the meantime, a bewildering variety of elementary particles have been discovered. Started with protons, neutrons, electrons, and then they just kept coming. And then in 1961, Murray Gell-Mann learns group theory and publishes his famous Eightfold Way, and wins a Nobel Prize for it. So this uses group theory to classify the known particles into elegant families described by group theory. It's a forerunner to the theory of quarks. It's a triumph for group theory, and today it's impossible to imagine theoretical physics without group theory. It's a key part of the curriculum, and it's been central to the advancement of the field. So, is category theory our Gruppenpest? It's a little abstract to learn. It's a little scary. But try this. This just doesn't work. It's a good model for what's going on, and it offers new tools. So why do I say... Oh, I haven't turned this on. That's why. So why do I say it's a good model? Well, most of you have probably heard of the Curry-Howard correspondence. So this gives us propositions as types and proofs as programs. This gives us a mirror between the worlds of logic and programming, and lets us translate backwards and forwards. But did you know this mirror has 3 sides? It's actually part of a larger Curry-Howard-Lambert correspondence, and the third piece is obviously categories. So Bob Harper likes to call this the holy trinity of computational trinitarianism. Sound rolls off the tongue. So given a type theory, we can create a categorical model for it, and given a category, we can talk about its internal language and internal. So that's a kind of type theory. We have an internal logic. The field that studies this is called categorical logic. So in a sense, we're already doing category theory, so we can't get away from it. We might as well make use of it. So, okay, quickly, some preliminaries. This ride will move quickly. Please keep your seatbelt fastened at all times. And you have a trainee driver, so now you're all terrified. But seriously, there is an actual category theory expert here. Please go to her workshop tomorrow. It's a tremendous opportunity. Obviously, I feel like a bit of a fool standing up here. Yeah, so, what do I mean all of? Surely that's impossible. Well, maybe the impossible is the only thing worth attempting. So, you might have seen this book. In the spirit of all stats, we're going to quickly cover the fundamentals of the field so that you'll be set to cover the rest on your own. So, we won't become instant experts. We're just learning the ABCs. So, there are a wide range of terms that get bandied around in functional programming. So they all come from category theory, and how do you go about learning them? Each one has prerequisites, and they have prerequisites. And if you're trying to read the NLab or some other source, it can feel like an unsolvable tangle. What's the best path to take through the subject to learn category theory? And the answer is a circle. Oh. Of course, it's not going to work. Sorry. Okay. Plays The Circle of Life by Elton John. And now we've got to put the slides back, sorry. There we go. So it's not the circle of life, it's the circle of universal constructions. So we start with initial objects and we go right down the circle to can extensions. So this will be our mind map for discovering category theory. Don't worry too much about the small print. It's also, we'll get to it. In fact, all of these things are equivalent, which is quite surprising. So meaning we can reformulate each one of them in terms of any of the others. So why are there so many? This seems really extravagant. Well, it's also a bit like the gears on a bike or the speedometer on your car. So we start off in high gear at initial objects. It's easy to pedal, but we don't have a lot of power. Initial objects are reasonably simple to describe, but often we can't apply them directly. We have to create a new category first. And for those who know about F-algebras, you'll have already seen an example. So we build this new category, and initial objects inside it are a nice way to describe recursive structures and folds in the original category. But we've got to build this new category. At the other end, we've moved to low gear. We have to work harder to pedal. We've got a lot of thrust. So these more advanced tools, like can extensions, can usually be applied immediately to a problem. And the flip side is that they're a bit more complex to explain and understand. So I'm going to assume some basic familiarity with categories, but let's take a quick refresher. So a category has nodes and edges, much like a graph, but we call them objects and arrows. I'll also call them morphisms. And we'll use both these notations for the set of arrows from A to B. We call this a Hopkins set. We've got a bit more algebraic flavour than graph theory does. So we've got composition and units, which obey the usual unit and associativity laws. We've also got equations between arrows. So we'll write these as commutative diagrams. This means we can keep track of the objects that we pass through. So the opposite category has the same objects, but the arrows are flipped. Categories really should be called networks. And this explains why they're so applicable in a whole lot of fields like electronics, chemistry, control theory, ecology, quantum physics, and so on. Basically, any field where you've got the words network or system is probably a good fit. But instead, of course, they're called categories, named after the different departments or categories of mathematics. Each has its own favourite kind of structure and comes with a corresponding flavour of structure-preserving function. So we'll be using the categories of sets, types, vector spaces, and monoids. And we're going to focus a lot on this one. So you can think of type as part of Haskell. So it's the pure, strict, and total subset. Lets us avoid some complications. But we can also think of categories as algebraic structures in their own right. So a set is just a category with no arrows, except for identities. So I won't write identity arrows usually. And what we call a pre-order is a category with at most one arrow between any two objects. So here we have a lattice of subsets, and an up arrow means is contained within or is less than. So we'll write A is less than or equal to B to abbreviate, to mean that this Hopkins set is not empty. Next, functors. So a functor is a way of drawing a picture of one category inside another. It's going to consist of two parts. We have one that sends the objects to the new category and one that sends the arrows across. And in order to preserve the shape, the arrows need to go where the objects go and need to preserve identities and composition. It doesn't have to be an exact copy, of course. It could miss some objects. It could collapse some objects. It could miss some arrows. You can't see, but there's pale lines here, the ones we didn't hit. And it can collapse some arrows. So here the two bars of the T are collapsed. So in Haskell, of course, what we call a functor is a functor from type to type. We've got some terminology for particular kinds of functors. So a functor that lands in set is called a presheaf. A Contravariant functor is one that starts off in an opposite category. So this will reverse compositions. A functor that takes two arguments, one contravariant, one covariant, is called a presheaf. It's called a profunctor. And the good old Hom set is actually the prime example. So why is this? It's because if we precompose with F, postcompose with F, that acts contravariantly. So B goes to B prime, B goes to B prime. Whereas if we act, so that's the action of F on the right-hand variable. And if we precompose, that acts contravariantly. So that's the action on the other side. So natural transformations, these are just morphing one picture of C into another. So each picture is the action of a functor, and we morph one into the other. So formalizing this, we'll say that a natural transformation should transform each object from F's picture into G's picture, but we have to be quite restricted in order to preserve the shape. So following an edge and then translating has to be the same as translating then following, and we call that naturality. And this has to do with natural constructions in mathematics. These are the ones which are also constructively valid, so you don't need to use the axiom of choice, basically. And naturality was invented to explain where they come from. Just a note that because we can now translate between functors, this means that the set of functors between C and D will be a category on its own. So in Haskell we approximate naturality with polymorphism, which is actually a stricter condition, because with polymorphism we're saying that we'll do exactly the same thing at each type argument, whereas category theory only asked us to that what we do at different types should be coherent. Okay, so finally we're ready for position 1 on the wheel, initial and internal objects. So a minimum element in a pre or partial order is simply an element that's smaller than all the others. We saw before a partial order is a kind of category. So how do we generalize the idea of minimal element? Well, less than or equal gets replaced with morphism, so it's clear that an initial object will have to have a morphism to every other object. And to get the right definition, we'll need to require there's exactly one arrow to each other object. So if this is initial, then all these composites will have to agree, and there's exactly one. So in type, this will be the empty type. There's a unique function from void to any other type, which we sometimes call absurd. There's only one possible function you can write. And dually, we've got terminal objects, which are the generalization of greatest element. And so that'll be the unit type in Haskell. And once again, there's only one definition you can write. So, okay, position 2, universal properties. Category theorists confidently assert that lots of different things that look entirely different are all products. What's the common theme? How do we ID when something is or isn't a product? And dually, what makes something a sum or a co-product? So let's think about products first. If you studied coordinate geometry at school, especially parametrization of curves, you'll remember that if we've got a point tracing out a path in R2 over time, we can break it up into its x and y coordinates, and then if we put these back together, we get the original function. So there's the signatures of those functions. So let's write that in our categorical formulation. So x coordinate goes from time to the real line, so does the y coordinate, and that should be isomorphic in bijection with functions from time into R2. So category theorists would tell us this property is actually what makes a product a product. So in general, we're going to have this situation. So the pair consisting of an arrow from x to A and an arrow from x to B is equivalent to one arrow from x to A times B. And for the co-product, you guess that we just flip the whole thing around. So let's step through the definition that category theorists usually give for the product. So product of A and B is another object with projections to A and B, just arrows, so that, and this is the universal property part, if you have any other object which also has arrows to A and B, we'll call them F and G, there's a unique arrow from that other object back to P with a special property, which is that the composites with the projections give you back F and G. Okay, that's quite a lot to take in, but if you squint, you'll maybe see that out of all the objects that have projection morphisms to A and B, we're actually looking for the terminal one. So this is another example of terminal objects. I've highlighted some words to point out where I'm getting the isomorphism on the previous slide from. So for all, and there exists a unique, meaning we've got a function, and the fact that we get our original F and G back means it has to be a bijection. So for the dual situation, we just flip the diagram. So a co-product is the closest object heading away from Q. So think of this as the closest object heading to A and B. The closest object heading away from A and B. And we call the arrows into the co-product injections. It's easy enough to translate this to code. Functional languages like Haskell were designed to express products and sums, so this isn't too surprising. So we take a tuple as a product. We have a forwards direction, which is just basically this tupling and its inverse, and first and second are the projections. We have co-products. Forward direction is pattern matching. Backwards is the constructors or the injections. So number 3, representables. Okay, so let's look at the isomorphisms for products and sums again. Both sides are sets. In fact, they're functors in X. So these are isomorphisms of set-valued functors. In both cases, we're being told we can trade in 2 things for 1 thing, which does the work of the original 2. So 2 things, 1 thing. We can talk about this situation more generally. We say that a set-valued functor is isomorphic to a partially applied Hom functor, Hom-R or Hom-R-. So we say this is a representable functor, and we say it's represented by R. So going back to products and sums, we see the functor on the top left. So this is a pair of morphisms, 1 to A and 1 to B, is represented by A times B. And a pair of morphisms, 1 from A and 1 from B, is represented by A plus B. Another interesting thing to note is at the top level, there's no sums, only products, which has interesting implications for functional programming. No sums means there's no choices to be made, so we've got a single constructor. So we can think of a representable functor as a data structure with 1 fixed shape. The type that represents the functor is going to correspond to all the positions within it. It's the type that indexes the data type. Conor McBride likes to draw an analogy with logarithms and exponentials and calls it the logarithm of the data type. So a stream is indexed by natural numbers. Every natural number corresponds to a position in the stream. And streams are isomorphic to functions from the naturals to A. So the forwards direction corresponds to indexing into the stream, and the backwards builds up a stream by iterating through all the positions. If you apply from to id, we get a a stream with every position labeled, filled by the label for that position, which is cool because the indexing type is manifesting as of value. Tuples are, right, I think I said that. Tuples are representable because they correspond to functions from the set of choices left or right. And we apply the isomorphism to the identity and we get our universal element, which is the, not on the slide, the pair left comma right. And we can combine these examples. So binary streams will have positions labeled by lists of left or right choices, and that's what the universal element looks like. The most important thing about representable functions is this apparently obscure result. It's called the unique lemma, and it actually ends up being the most widely used result in category theory. It's also been called the deepest triviality known to man. So let's pause a minute to unpack what's going on. So these two guys are functors. So we're talking about the set of natural transformations from a partially applied Hom functor to f. This naturality condition is very rigid, and in this case there's only one degree of freedom. We have to map the identity on R somewhere, so we choose an element of the set FR, but once we do this, it turns out naturality means we already have a full definition for all objects. Our hand is forced, so basically to get the definition of any other object, we use fmap to that universal element. Okay, so done. We move on to limits and colimits. So let's think back to products. You're possibly already wondering, can we generalize to a product of many objects? Let's try and do one better. So we can think of two objects in D, so that's C, that's D, as the image under some functor of a category which consists of just two objects, which I draw as unlabeled dots. We'll call this the image a diagram of shape C in D. So we can replace C with another category to get a diagram of another shape. The closest approximation to the diagram will be called the limit. And I mean this in the same sense as we had for products. The only proviso is if this diagram has arrows in it, then these projections have to be coherent in a sense because they're going to interact. So in other words, if we end up forming any triangles, they'll have to commute. So straight away we've got n-ary products. A null-ary product is the same as a terminal object. It's a limit of the empty diagram. Oh, there's squares around the categories that you can't see. No. For parallel arrows, we get what's called an equalizer. Let's draw it up that way. This is the categorical equivalent to an equation. In sets, these will be equations. The set of solutions to an equality between two functions defined on X. And if our programming language has dependent types, then we can express an equalizer using equality types. Another important limit is the pullback. This time our diagram has two objects with a morphism to one in the middle. In set, this will be a subset of the product where the two sides are required to agree after applying two functions to a common codomain. So a great example of this is the inverse image of a set. So this is the set of x's and y's such that f of x equals y. So it's the equalizer of f and the identity function. If we flip the diagram around, we get colimits. So this is the closest object heading away from the diagram. So we've got notions of co-equalizer and push out. So in set, these correspond to quotients of a sum. In other words, we're partitioning up the set by an equivalence relation and considering the equivalence classes. These don't exist in type if we mean Haskell, Agda, or Idris. But if we've got homotopy type theory, then we have quotient types. So summing up, a limit is like a generalized product where the projections have to satisfy some compatibility conditions. And a colimit is a generalized sum where the injections are forced to agree by taking equivalence relations. Interesting thing is we don't need to consider all limits. We can build all limits as long as we've got equalizers and products. And similarly, we can build all colimits if we've got co-equalizers and co-products. Okay, so let's have a look at adjunctions. So we've got a functor from C to D. It's natural to ask if it's got an inverse. In most interesting cases, it won't. So we've got to ask for the best approximation. So these are called adjoints, and they come in pairs, left and right adjoints. So what's happening is the D arrows from DC to D line up one-to-one with the C arrows from C to RD. So we say L is the left adjoint to R is the right adjoint to L. So let's look at a couple of examples. So the functor that makes a vector space out of a set of basis vectors is called the free vector space functor. Its opposite, which are called U, turns a vector space into its underlining set. So it's basically the identity function, functor. So the vector space R2 is free on the set of basis vectors I and J. The linear map, a linear map from R2 to R3 consists of a 3x2 matrix. And this matrix is equivalent to the pair of column vectors that are the images of the basis vectors. The next example should be new and dear to functional programmers. Functors out of a product correspond one-to-one to their curried forms that take one argument at a time. So categories that have an adjunction like this are called Cartesian closed, and under the Curry-Howard-Lambert correspondence, they correspond to the lambda calculus. So there's important theorem that right adjoints preserve limits and left adjoints preserve colimits. This is handy because it lets us see at a glance that some interesting isomorphisms hold. So I know immediately that the underlying set of a product is the product of the underlying sets, and that the free monoid on the empty set is the empty set again. Okay, monads. These are of course really important, but functional programmers already spend too much time talking about monads, so I'm going to skip it. We've met profunctors before. No. Is there something like a limit for profunctors? Well, okay. If we've got, I'm running out of time. If we've got a profunctor S and a morphism from A to B, there's two ways to reach a SAB. We can start with SAA, apply F to the covariant argument, or start with SBB and apply F to the contravariant argument. So this makes a little diagram. If we do this for all the arrows in our category, they overlap to form one big diagram. We'll take the limit of that big diagram, and that's the end of S. So I've just drawn one there, but you've got to imagine there's a lot. The notation invented by UNITA looks like an integral sign because, in a sense, we're integrating over the whole category. It's a kind of infinite product with projections. Dualizing, we've got, of course, the coend, which has injections to each SAA, and then notation has a parameter at the top of the integral sign. Ends are great for two reasons. The first is they've got an easy encoding into Haskell. We model an end as universal quantification, and similarly a coend becomes existential quantification. This is similar to what we had for natural transformations. The Haskell version is actually more stringent. Second reason they're great is they're really easy to work with. So the whole coend calculus, which mysteriously behaves a lot like integral calculus. So we've got a rule of interchange of integrals, which is a lot like the Fabini theorem. So this makes them, in some ways, better behave than limits. So here we have the UNITA lemma recast in end and coend form, which is quite interesting. Here. So what I'm saying is for any pre-sheaf, we've got a unique way to write it as an integral over representable functors. So the representables are and this is a unique way. So the representables are, in some sense, the basis vectors of the pre-sheaf world. So this is sometimes called the density formula. And we use this calculus to, hang on. So, right, natural transformations actually appear as a kind of end. So we can use, so I lost my place. We can use these calculus to work out isomorphisms between types. So here, I'm not going to have time to go through this, but we apply these rules along with things like our uncurrying and initer and so on. So yeah, and we can show things like this. A product F to C is the same as this type. And in a similar vein, we can prove that the pair of getter and setter is isomorphic to this, which if you know the lens library in Haskell, you would have recognized this is the somewhat mysterious representation for lenses in that library. So it's basically, you just keep applying the same rules and it's a bit of a longer calculation. Okay, 0 minutes left. Can extensions. The problem can extensions try to solve is, so we've got a functor f defined on C, we want to extend its domain of definition to a bigger category D. Actually, we won't insist on bigger, we just mean another category we get to via G. So we think of composing G as restricting, composing with G as restricting to the smaller category C. In other words, we're trying to find a functor K from D to E so that doing G then K is the same as doing F. It sounds like a hard problem to solve, but the opposite problem is easy. So if we've already got a solution, K, then we just, K composed G gives us back the original F. So we know that, where can we go with this? We know that adjoints gives us the best approximations to an inverse problem, so let's try that. So we call the left and right adjoints to the restriction along G, the left and right can extensions, and we call them right lan and ran. So what's the rest? Oh, okay. There's a box here, which is a category D. There's a box there, which is a category C. And there's a box there, which is a category E. So we've got an object in D. Sorry, some of you have to go. I'll keep talking until someone keeps me off the stage. Yeah, okay, no worries. Yeah. Cool, thanks for coming.